Good morning, everyone. Thank you for being here today. We welcome you to the second Transversal Installation Competition Conference, Rethinking Materials by the architect Roberto Naboni. Before we begin, we will give you a short introduction, followed by the presentations, and to conclude, we would like to have a Q&A section. First, we want to introduce ourselves. My name is David John, and together with my colleagues Viviana Velázquez and Laura Guerra, we are the founders of New Art Competitions, and we will be hosting all the activities of the competition. On behalf of the New Art team and the Transversal Festival, it is a pleasure to have you here, and we are more than happy to be able to present, meet, and also learn from the great work of the architect. New Art Competition is an organization focused on architectural competitions with the primary goal of promoting art, innovation, and creativity to architecture for students or young architects. In this occasion, we are collaborating with Transversal Architecture and Design Festival, organized by the Panamanian College of Architects, to create the Transversal Installation Competition, a competition aimed at design and build a temporary installation to be exhibited in January 2024.
As the next point, we want to talk about the background of our guest speaker, Roberto Naboni, who holds a PhD with honors, is an architect and associate professor in computational design and digital fabrication at the University of Southern Denmark, where he leads CREATE, the computational research in emerging architectural technology and engineering. His research, published in more than 70 books, journals, and conference articles, focuses on evolving experimental architecture and design, employing integrated design, advanced manufacturing, and novel material systems. He previously co-founded and led ArtLab at Politecnico de Milano and collaborated with international research centers, architectural firms, and tech companies, including ICD ITKE Stuttgart, AAVS School, Skidmore Owings and Merrill, EMBT, Stefano Guerri Studio, Ecologic Studio, Odico, and WASP. Without further ado, we officially welcome architect Roberto Naboni.
Yes, thank you for the introduction. It's a pleasure to be here and to share my work or the work of my research center. I'm going to share my screen, and please let me know if... Are you visualizing my slides right now or my desktop?
Your slide, the first image.
Okay, fantastic. All right, let me just put this down. All right, so yes, thank you for the introduction. I'm not going to reintroduce myself with a full biography, but indeed, I'm Roberto. I like to call myself experimental architect because most of the projects I work on are not actually professional works, but I would say academic works and research projects. We do build, but we do build in an experimental way, and that is what I'm going to talk today, to speak about today. So I'm based at the University of Southern Denmark, where I'm leading CREATE, and I will talk to you a little bit about what CREATE is, and then going into some of the projects. But the idea is that I'm going to today talk about how we can rethink materiality and focusing on the circularity of construction, especially using one of the most important bio-based material that we have, which is basically wood. So very briefly about CREATE, we have been based here at the University of Southern Denmark since 2018. I've been funded this, so I moved to Denmark. I was back then in Politecnico di Milano. And when I moved here, I decided to open basically a new research area on computational design and digital fabrication. And the reason why I moved here is that here, this part of Denmark where I'm based, it's basically the robotic valley of Nordic countries in Europe. So as an architect, I decided to move to a faculty of engineering because I like the environment of being working with technology specialists and doing architecture within an extremely technical environment. Just very quickly, we are based at Odense, which is the third largest city in Denmark. And that's basically what you see here on the left. It's our headquarters, so I'm in that building right now. Also, our labs are in there. but also we have a presence in Copenhagen, which is just an hour away. Copenhagen is the world capital of architecture. It is well renowned because of its architectural firms and urban environment, which has a very important outlook on sustainability. And there we have a space, an office space in Block Sub, which is this fancy building designed by Oma and Rem Koolhaas on the main canal, which is where we have our connection to the world of architecture. So I work in between these two worlds, you could say, so the robotic capital of Nordic countries, and then the world capital of architecture for 2023. So I don't want to go too much into detail, but all the work I'm going to present is basically part of the team that you see here. I mean, the team is slightly different as for now. These are basically researchers, PhD students, and so on. I'm leading the group. But what is important to mention, which is not clearly indicated in this slide, is that we are not only architects. We are architects. We have building engineers, civil engineers. We have robotic specialists. We have mechanical engineers. And the reason for that is that all we do, it has this high concentration of technology and very technical stuff. And we like to develop our projects in an interdisciplinary way. So just keep that in mind. And what I want to introduce to you regarding Acreate's work, but also the team we work with, is basically why we are actually working in our area. So we try to motivate our research and projects as much as possible based on sustainable reasons. And we know that as a building sector or architecture, construction, engineering sector is not doing particularly well into the game of sustainability. The building sector is responsible for 39% of carbon emissions, is responsible for 30% of the overall extracted natural resources, and 33% of waste generation. This number is specific for Europe, but this is more or less the kind of impact that we have over the environment. So we try to look at these problems in a proactive way. We develop new technology and new design approaches that try to mitigate this, and where possible give perspective to not only reduce but basically become neutral towards the environment. One of the main resources that we have, and I'm going to talk today, is basically timber. Timber, as we define it here, it is essentially a carbon store, which means that being a bio-based material, timber basically absorbs when in the form of forest, in the form of wood and trees, it absorbs basically carbon. And you could roughly imagine that depends on the species, nearly 50% of the makeup of wood and timber, it is actually made of carbon. That means that around 1 kilogram of wood is equivalent to 1.8 kilograms of CO2. And this is extremely important as a resource. Of course, all of you that are architecture lovers are well aware of that. Something that is a little bit overlooked sometimes is that we should not only design for timber and employ more timbers, but we should be more considerate in the way we use it. We need to extend the life cycle of timber to make sure that it doesn't get basically dismissed and doesn't get basically in landfill, doesn't get basically incinerated, because otherwise all of the CO2 would go back. So one of our main ideas is basically extending the life cycle of wood, and the projects I'm going to talk about basically look into this. Something extremely important is that wood is a renewable material, so we know it has a grade of renewal, and we do not extract basically resources that are not regenerated. But nevertheless, we need to be very careful about the renewal of wood as well. And this is because forests are not an infinite resource. Forests are, of course, the largest CO2 absorbing agent. With this number of 7.6 billion tons of CO2 that is absorbed indeed yearly worldwide by the forest ecosystem. But that also, and that is also basically the kind of CO2 that you might in perspective use in your buildings. the most important thing is basically to look into this forest as what is called basically sustainably managed forest, and we need basically to balance out the demand and supply of timber. This is one of the challenges that we have, and especially in a European context, we have also been conducting some studies to understand basically how to have basically these cutting patterns for forests that are not completely cut through, but actually allow for a continuous regeneration of the forest. This is a very important and difficult topic in itself. But what I want you to think of is that we need to think of the quantity of forests and the quantity of wood buildings as a larger carbon sink that we want to preserve as much as possible altogether within the environment to be absorbing CO2. So what we try to do, given this motivation, is to extend the life cycles of wood, which is key to decarbonation. And how to do this is basically enhancing circularity. So we look into reconfigurable structures, which in our mind is an extension of what normally would be considered reversible structures. We want to eliminate waste with our design of building components, which are thought for multiple life cycle. And we want to increase the carbon storage within construction without any performance loss, which means that we do not want to just replace building components with wood, but we actually want to make them still efficient from a point of view of material usage. So I'm going to present now some of the research projects, and especially this one, which is reversible robotic timber beam, has been our first project in this the line of investigation. The motivation were indeed carbon storage and circularity of resources. We look into the use of collaborative robots, and basically this is how we all started in our investigation on this topic. So what we did basically in this project is producing this sort of beam prototype. It is what technically is called a discrete assembly, meaning that we get together structural elements out of smaller elements, and these smaller elements come from this kit of discrete parts. I like to explain this as a sort of Lego kit for wood construction that has basically this range of components. If I remember correctly, they're 11 or 13. They share more or less the same kind of shape, and they have these holes, and these holes is where you can get different connectivity patterns. So something that we did here to produce this sort of Lego elements is to run industrial production with CNC machines. So we had over 1,000 of these components, which are generic, and then these components are used specifically for a project that we built. So this is what we typically call a computational workflow. You see on the left side what we named here as design digital twin, and on the right side, robotic assembly digital twin. I'm happy to take questions later about the specificities. What is important to mention here is that all of our projects, which are research-based, start exactly from these workflows. So the way that we want to innovate is establishing continuous digital workflows where there is no information loss. And here you can find in the top part, basically our voxel-based design and structural optimization. And in the bottom part, you can see here basically material processing and digital fabrication. So we have a digital and a physical counterpart, which gather together to do performance-based design, discretization of these elements. So this is a workflow that applies to a number of cases. We've used it to produce this reversible timber beam. Now, I'm not sure we have the time to go into the details of this, and maybe it's a little bit redundant, but something that is interesting here is that we basically use topology optimization, which is a technique to generate efficient structural forms, and then we discretize it in what we call voxel attributes. A voxel is basically a 3D pixel. A voxel can store information on digital modeling, and this is basically used then to do a number of operations for this design process. The interesting thing here, at least for us, is that we have this direct connection to the robotic system. And the robotic system, I'm going to talk about it in a second, it is basically where we can fabricate, we can manufacture with digital information. We do not really have a translation between design and construction, and that's where we are aiming to in the long perspective. So we developed, in collaboration with SD Robotics, a new type of robotic effector, robotic tool, which is combined, as you see on the left, basically from an electric gripper. This is a commercial product where you can grip and basically handle elements, but you can control all the kind of dynamics of the system because it has sensors and so on. But also you have basically this red element on the right, which is an electric screwdriver. And we were basically the first one using actually putting together, not only assembling in a dry way timber structures, but also fastening them together with a full robotic process. So there is a small video here where you can see how does this work. We have these small elements. We basically pick them from a magazine, basically from a part of the setup. We place it in the right space, and this is coming directly from the digital model. And then the robot suddenly switch into basically the other tool and basically is testing all of these elements. So as you can see here, we basically produce in this horizontal way, and I would say that we kind of design our elements to be robotic friendly for assembly, and that was the point of departure. Now, and here is where you see why I need an interdisciplinary team. We then decided, after these experiments, building up this BIM, that we need to make the process most consistent. We had basically hundreds and hundreds of holes and elements. You gather up basically tolerances, and we need some feedback. So we decided basically to work on this development of the robotic cell. So that's quite funny because as designers, we understand that we need to develop technology sometimes to do what we want to do. So we basically made the second project, which is about robotic timber reassembly. And here we use a similar setup, but to do assembly, disassembly, reassembly. The main innovation from a technological perspective is that we basically inserted this, where you see this blue LED light, we inserted a wrist camera. This is a camera which allows us to scan the elements and gather some information. On the other hand, we also added basically this red element that you see on the top, and that's basically a switch which allow us to switch basically from automated operations, so the robot running it by itself, to manual help. So when something goes wrong, we have redundancy in the process. We can actually help the robot out completing a task, because it might sound trivial as an automation project, but actually it is kind of complex to put these structures together. Once again, this is a workflow diagram. I don't want to bore you with too many diagrams, but something important here is that we're only looking here on the robotic side of things. So what this diagram is showing to you is that we have these pick and place targets in the beginning. The robot basically, it is executing the assembly and then positioning an element and then taking a camera snapshot, basically a picture of the component. By chance, I have one here, so I can actually use one of these. It's placing this and then taking basically a camera snapshot and individuating where the holes are, and then generating the geometrical coordinates of this and updating a digital model. So we call this as digital twin because the digital process and the physical process are interacting and updating in a bidirectional way. And then on the basis of this, basically, there is a screwing operation. The screwing is fixing these components, and these components, when they're fixed, you just move on to the next. When there is some problem, we have a force torque sensor, which tell us, okay, something is wrong, and then we call for human interaction. Why this is important? Because it makes the assembly as absolutely, let's say, consistent. So we have basically no failure in this. But also this makes possible to do this assembly process. And that's very important for circularity, because if you can put wood into a structure and this structure can be automatically assembled, but can be also automatically disassembled, then we can move towards a sort of robotized paradigm of construction where circularity, where basically building materials such as wood are actually just flying from one building to another, and they can be reused just as a Lego kit, as a Lego pieces in different projects at any point. So this is basically a quick animation. Yeah, it's working right now. Sorry, I will go back to that. Where you can see on the left side, basically the I need to run this. You can see on the left side the assembly process that is made automatically by the robot. And then you can see on the right side, actually, this assembly process. We basically run this couple of ties on these smaller elements. And what happens there essentially is that with this move, we can coordinate, we can actually correct the coordinates. And you can see here exactly how in this specific hole, it was actually updated the system. So this is a number of very small open structures that we built with this system. The reason why we do this is actually to prove scientifically concepts. So we have scientific papers that describe this, and we like to look at the data. So what you see here is that almost all the attempts of assembly actually require the camera because they are over the threshold of 3 millimeters, which would be the maximum deviation that we can account for without using a camera and having no problem in the assembly. So this just to prove that actually we need the system, we need the camera is working, everything happens successfully, and we need this kind of feedback. And this gave us basically, I would say, the technical framework to investigate more on architectural level what we want to do with this. So last year, we formalized our architectural proposition into what we call Recon-Boot system. Recon-Boot system, it is basically upscaling these experiments into a system that has 3 pillars. The first pillar is basically tectonics, basically looking into multi-resolution timber framing, which are based on construction kit of reusable wood elements. What does that mean? We're working with timber framing, but timber framing that don't look like typical timber framing, and they are completely reversible, and they are actually designed for that. The second pillar is basically cyber-physical construction, which means that we're looking into robotics, we're also looking into mixed reality, and we're looking into essentially having this digital design process that is directly connected in both directions, from design to assembly to updating models using this technology. And the third pillar is data. We strongly believe that we can achieve circularity of material, so reusing material or preserving the use of wood within the construction and the built environment for longer time, so extend the life cycle, as I said before, if we are not only transferring material from one building to another, but if we are capable of retrieving data along the process all the time. And because of this, we started basically marking with QR codes all of our elements to be able to specifically individuate an element within a structure and gather all the material data and the history of such element. So I'm going to show you now a number of projects which are Recon-Boot projects. The first prototype was basically exploring the possibility for XR, so extended reality collaboration. And we basically built this kind of timber frame wall, which, as I said before, is multi-resolution because it can vary in terms of amount of elements according to your specific structural requirements. So we had this process of co-design between 2 users that were using this mixed reality headset. These are HoloLens, maybe you're familiar with those. They've been manipulating this kind of simple geometry through control points. And out of that, basically, then we have a pipeline of voxelization, which generates such a structure. So we do have years which we switched here onto fabricating these elements with robotic setups that we have in Create Lab, where basically we generate these elements. These elements are probably different. You realize probably that they're different from the previous ones. We now have this kind of shear locks interlocking system, which allow us to transfer some shear, but also some moment during the assembly, but especially later on. And then we have on the right side, basically this kind of assembly that here was done manually through mixed reality. So we basically developed a mixed reality interface straight out of Grasshopper, and using this HoloLens, you receive this information on the assembly instructions, where you have to fix the bolts, what is the kind of element you need to use. You need to remember these are generic elements which are basically placed in a very specific configuration. And of course, you can interrogate the structure during the process to get a little bit the overall picture. So through this, we basically built this prototype, which is experiment, experimental in the sense that it's the first time that we did it. It was successful. It shows a good degree of, let's say, structural integrity, but also it's our way for this project, not only of showing a nice piece of exhibits, which goes into exhibitions, but also this is our demonstration. It's where we observe and we comment and we move on for the next project. So these are just some of the images about that. But then we develop a new project, which is Recompute Proto 02, where the idea here was to extend and fix some of the, let's say, the details of the project in terms of building technology, but then engaging more clearly with this sort of data-driven reconfigurability. So now, when we look into this idea of circularity of material and bringing information about material along, there are some concepts that exist. There is the idea of a material bank, where existing buildings are considered as available stock that can be mined for future construction. So that's the definition from literature. I hope I'm not too academic. But then we have this concept that is very popular right now in Europe, is about material passport. And basically this is a sort of, how to say, archive that is storing all the information about the construction history of the materials for future use. And then we have this idea of material market. So you can actually go online and shop used materials. When we did this literature study, we figure out that all of these concepts are implemented at the end of the life cycle, so at the demolition or pre-demolition phase. And this generates information that is a static database that is archived. It is updated for archive file formats, which is how to say, it is just some information that is not directly attached to a material. So it has some degree of vulnerability, but also it is detached basically from his physical counterpart, which means it cannot be updated on the go. So we came up with this idea of material digital twin, which is a dynamic material database. It has a permanent link through these QR codes, as you see in the pictures. So when you scan one of these codes, you get all the information about it, about that specific element. And then also it established basically this bidirectional communication between the computational environment and basically the fabrication environment. So it is something that you bring along, and it is easily accessible by both humans and machines, because both camera vision and both your phone and both HoloLens headsets and so forth can scan this at any time. So it means that the information is readily available. So this is just a diagram that shows some of the properties of this material digital twin. So it contains information about the robotic fabrication. When you fabricate digitally wood, you need to kind of tailor your setup, your tools, your speeds, and your feed rate to the specific material. And sometimes it takes some trials to adapt that. It's important to store that for future refabrication purposes, but also information about the assembly data and the operations. So and eventually also the disassembly data. So this is all basically led, and this is where the material digital twin it comes to an end. So this is basically some images where you can see we also tectonically extended the process. We started to introduce some cantilevering, so trying to test this kind of nodes for more structurally demanding scenarios. And this is a breakdown of all the, how to say, the information folders or menu that you have within material digital twin. So there are information about the ID of the elements, the structural performance, the circularity, robotic fabrication, assembly, use, and operation. So for example, we run structural analysis, and then we set up this kind of prototype to we'll configure it in such a way that we do not overuse the material, so that there is no fatigue and they can be reused in other projects without damages. And we store the specific information about this within the material digital twin of these elements. So the kind of reddish elements which are more stressed, they will have basically a utilization information that is stored within the material. So structural performance, material data is all in there. So how do we fabricate these elements? As I said before, we use a robotic setup. This is in my lab, is one of the robots that we have. We have basically this milling robot, which is picking up different tools for placing holes, then for creating this kind of shear keys elements. We use a V-type kind of end mill, and we have this kind of indentation. And then following this, we have another step with a flattened end mill, which is basically allowing us to clear the kind of leftover material and having these super precise elements out of the robot. So these are generic BIMs, and then they're cut into parts. All of this information about the machining, so it is stored here. So basically the information about the fabrication tools, the toolpath length, the toolpath time, the cutting speed, and so on. And maybe this gets a little bit too technical, but believe me, if you engage with fabrication, you would love to have those information already stored along with the material, because it saves a lot of time into processing the next elements in future. We don't know. Maybe 40 years, someone else is going to remill these elements, and therefore it's important this information is stored. But then we have the robotic assembly setup, which was slightly updated here. You see here now in the background, we have information about our digital twin. And in this case, we had a collaborative human-robot interaction, which means now it's robots and humans collaborating on the process. Now, this looks a little bit like an over-sophistication, but it's basically what we have in another lab here at SDU. We have these collaborative robots working alongside with the human operators, and then there is basically PC servers that sends out this information in real time. So you get instructions, and you can see here basically how it was made. The robot pick up a place. The human operator has a very specific information where to place these embedded nuts. So here is where generic elements get to be specific. We want to have embedded nuts because then the robots are going to screw exactly these elements where there are these embedded nuts. So we kind of created this assembly line where robots and humans collaborate, and you can supervise the project by looking at this screen in the background, which has updates essentially on and statistics about the fabrication. So this starts looking a little bit like an industry, which I mean in a good way, because it means that we are basically expanding on the level of automation and productivity that we have. But this information about the robotic assembly, the location of the types, the type of elements, the length, the diameter, basically of the nuts that we use. So all this information about the assembly are stored within the material digital twin. As I said before, you can interrogate this. So in the first version here in this project, we use basically this kind of this laser cut QR code to actually paint over these elements, and then this element could be and are interrogated through at any point through the structure, through using this basically phone or whatever you want to interrogate the QR code. So there is this material digital twin. This is basically a description. How does it look like? You can see here on the right, you have basically some data and some drawings that give you information. And then we have on the left side, essentially all the database that you can download. The cool thing is that we use a speckle here. It is basically an application that allows you to do interoperability between Rhino, Blender, BIM software. Here we use it actually to transfer basically data between all the phases. So it is completely cloud, completely accessible online. These are just some images basically of the prototype. And here you can see Anya Nagelina, who has worked on this project along with Roberto Cognoli. Anya, which you see sitting on the structure, is doing her PhD on this project. So she's eventually the expert of the system, and the PhD looks into developing this kind of timber framing system that is completely circular through new technology. We have extended this approach to another project, which is called Recompute Slab. I'm moving on a little bit quicker here. I think you got the point. We think that there is this run to use more timber, and there is engineered timber as such that you see here in the picture that is used in these massive panels for walls and slab systems. We do think that that's an overuse, an overkill. You don't need all of that wood. So we wanted basically to kind of find with our Recompute system a sort of replacement for that. So we came up with the idea of a reconfigurable timber frame slab made of discrete timber beams that are reversible. So these are, again, coming from the same system, and we're just extending with other joinery. This is one of the drawings that shows how the system works. So you still have these vertical joints that you see here in the center, but also we started having this kind of wood screw on the side and so on, and basically making this 100% reversible, but also reconfigurable at any point. Once again, computational design workflow, we have some foam inputs, we run a finite element analysis, we generate information about the principal stress trajectories and the magnitude of stress. We voxelize the information, we store it within the digital model, and then we generate basically a materialization. So we invented this term, which is called, or we adopted this term, which is called Maxel, is a material voxel, is where we go from a digital representation to a kind of physical representation of 3D elements. And that's where we have all the connections that are figured out. So this is getting a little bit more complex. So on the right, you see here one of the timber slabs that we produced, so recon slab, that is suspended from a crane. So it might look small, but it's not that small actually. And you see these chunky solid elements, that's where it's supposedly, that's basically mimicking supporting points. Here you can see the process of optimization. We have this maximization process, which basically generate iterative subdivisions in order to achieve a certain amount of displacement, which is within basically the maximum tolerated displacement from Eurocode, which is 6 millimeter in this case. How do we do that? We basically have this, the maximization process comes from the fact that if you have to manually run, let's say, the design of such timber slab, it would be very arbitrary. It is very easy to make a timber frame slab out of beams if you have two supports. When you start having weird shapes and kind of multiple supports and different kind of conditions, you want an automated process, but you also don't want to model one by one these beam elements. So we came up with this voxelization system, which has some properties, and through subdivision, we generate in seconds, basically, this layout. Now I'm going very specific. With maximization process first has this voxel with stress attributes. You can see here the direction of the stresses. And then this is transformed basically in X and Y direction beams. These beams are evaluating their neighboring areas through algorithms. This is completely automated process. So this is a breakdown of the process. And then here there is basically an extension and shortening of beams to make sure that there is a full solid kind of a frame that is automatically generated. So this is the extension comes from an investigation of the the neighboring voxels and given structural continuity according to stress paths. And then you generate basically this clustering of elements, and finally you get all these kind of connections in place. So the difficult part of working with complex timber structures is that you need to have a clear load path, and the load path, it is actually efficient if you have good connectivity, and the connections and all these joints have to transfer loads in a smart way. So eventually, after all this process, you get this kind of layout, and this layout essentially has a secondary kind of line of beams, which is on top, which is basically made to connect together all the elements. So long story short, this is a flexible algorithm that in seconds can give you structural solutions that are custom and are efficient for any type of boundary conditions. So what you see here on the left is in this pink areas is where you might have wall or columns that are supporting, and then you can get basically all this layout and setups automatically generated in seconds, which is within the serviceability limit for wood slabs. So we produce one of these options. These are David and Giuseppe in Create Lab that are actually assembling the structure with mixed reality. And these are just some of the pictures of the structure. It is something that is functional. It works completely. I think it has a very peculiar kind of aesthetic, but aesthetic is just the result of the process. We are not going one by one to say, okay, here we put these elements, and this is structurally efficient piece. And also the kind of balls that are put in there, they're optimized in their placement according to this process. So some more pictures of this, and this you see an overlay where you can read the primary beams and the main structural direction. And here basically you see the three of them structurally testing in a non-destructive way the slab in itself. So what did we achieve here is basically, and just to give you some conclusion out of this, because I think we will run soon out of time, so I have a few minutes to wrap this up. We have achieved with Recon's Lab a quick design workflow, which in sub-seconds actually generate structurally efficient options, which then can be investigated further, but that's very good for design engineering. We have built up this prototype, which is true 3 by 2 meter multi-resolution framing, which has a reduced kind of deflection, so we can use it, we have in the lab. And then we, of course, I've done this as a reconfigurable construction kind of setup. So we have 60 meters of primary beams, 86 meters of secondary beams. This is equivalent to 378 kilograms of CO2. And all of these elements have been used for other projects. So now we built other 2 slabs because we keep refining the process. And now we're building the 3rd one in this week because actually this is part of a larger element. So just to wrap up, so we've seen here, we have these tectonics, construction, and data pillars, which we keep together. So I assume that all of you, or most of you, are architects, and your take on technology might be on the design and modeling kind of side of things. What I find is very important is that if we want to push new type of architecture, we need to experiment with the construction technology. Robots are some of the technologies that we use, but also we need to keep in mind that we need data along to ensure circularity and to ensure that we have we can preserve the material in the built environment for longer and ultimately reduce our impact on the environment. So I'm about to wrap up. Basically, with this idea, right now we're working on this prototype, which is the slabs that we are fabricating are actually part of this design. It is a full, I don't have yet a name for this, I don't like to call it pavilion, but this is a fully functional structure that comes from these reversible elements, and we're going to reuse elements that of the previous prototypes as well. So we want to prove this works. We are going to build this at STU in our campus, and right now we basically have already 2 slabs and we have 1 facade. And here I can show you basically the new slabs that we have actually made, and some also of the detailing that we have evolved for further. So now the whole system actually has a number of connections that I'm not showing in this presentation, which we have tested over the summer in our summer school. This informs our finite element simulation, and therefore we can predict the structural behavior in such a precise way, and this is an ongoing process. You can see here the QR code. Another innovation we have right now, we have actually QR code printers that place them directly. So this is actually used, and if you're passionate about this, you can follow up our publications over the next year. We now basically use this QR code to store all information through Speckle, and Speckle is used and connected to an online database. So we have an online database that when the robots are putting together structures of the walls, and when humans with HoloLens are putting together the part of the structure of the facades, it gets automatically updated. So you have this kind of control room over the website where you can see all the statistics about the fabrication, the assembly, and that's basically the kind of scientific results that we want to build along our architectural prototypes. So that is all from my side. This is again my name, email, our website, and social media account. And I'm very happy to take questions, and but of course also feel free to reach out on this social media platform, and of course follow us on Instagram, Facebook, LinkedIn, and so forth. And thank you for the attention.
Well, thank you very much, architect, for sharing your experience, design, and architecture throughout the construction process. For me, and I'm sure for the students and participants, we are delighted to be able to learn that behind an idea, a concept, there is the most important and real part of architecture, the assembly and disassembly process, the construction process, and all the construction techniques, details, and methods such as robotic system. We are surprised by how important good layout work, method, or organization can greatly impact the final work, and such as the construction, the layout method is equally important to express the construction of this idea in clear and secure manner. So thank you very much, architect, for your time. And now we will move on to the questions and answer session. If anyone has a question, you can raise your Zoom hand. Yeah, Stephanie.
Hi, Roberto. Can you hear me?
I can hear you, but I cannot see you. But I think we can
well.
just voice.
Do you want to see me? I don't know if I have to start the video.
I mean, it's not as you like.
Well, it was mind-blowing. Actually, it was mind-blowing because, as David said, for us as students, we usually don't see the construction aspect as much as we would like to. But first, I have many questions. But first, I would like to know what are some of the considerations that you have in terms of the maintenance of and maximize of the timber lifespans, because at least in our country, well, obviously there are different climates, but at least in our country we have a tropical rainforest, so we use timber, but we don't use it as much as we used to. So what's some of the considerations that you think we could have for use it in the competition that we are going to participate in?
Okay, thank you for the question. So I would say probably my perspective is it is a bit Eurocentric on that, but I can share some information that I still find relevant on an international kind of level of thinking. So what we realize here is that, or actually I do not have it in this presentation, that we made a map of countries that have of the need of construction of timber for construction for country and the available amount, and it completed this balance. So long story short, we have not enough wood for fulfilling all the need of construction. So first thing is you cannot construct only out of wood, and that's why in my research center we also work with other materials which are not in this presentation today. Because of that, it is extremely important that we are efficient in the way we use wood, and that's why we have all this structural optimization. I haven't stressed too much. It is an underlying, let's say, paradigm within all the work of Create to have this structural optimization. So I am an architect, but I like structures a lot. And for me, designing, there is no architecture without structure, there is no structure without architecture, which means I suggest you also get good at evaluating structures, not only aesthetically, but efficiently. So you don't want to overuse material. That is the first information. The other information here is that you want to think of way of reusing wood. This project or this recompute system is about design for disassembly, or for what, as we call it, reconfigurability. So it is so easy. A robot can scan and disassemble, of course, still research, but can basically disassemble and put a structure together again in different formats. You might actually edit structures. So you might actually convert, you might reinforce them, you might. So that is super interesting. And I suggest that you look into wood as a material that has to be easily deployed and taken away and reused, and can be stored and reused in different projects. So I took it, I would say, a little bit, I made a killer loop about the question, but these are two principles. So structural efficient and reusability of material. If you can ensure that, then you're pretty covered with your kind of sustainability, sustainability goals that you want to achieve. I'm simplifying things, but the main thing is never get wood rotten, never get wood burnt. We need to use all of the wood in our construction projects, and that is basically something that you could take into account for the competition.
Thank you. By the way, I couldn't help to see a little bit more of your work, and I saw that you and your team have made research with concrete. How was this process like? Did you follow the same steps that you did with timber, or what it was like?
No, so this is another important point. I think sustainable construction, it is geographically specific, it is material specific. So when you design with concrete, I believe, of course, there is a lot of research right now that is going on about taking disassemblable concrete structures or reversible concrete structures. On the other hand, we use reinforced concrete because we can generate any shape, and we can have structurally continuous elements. So it is a bit of a mix. What we do there, we do design for longevity. So in my opinion, a basic sustainable strategy is to have structurally highly optimized structural design for concrete. That's what we do. And we are looking into making sure that we use as little material as possible through 3D printing, and that is our main research line. But the perspective is that this element will withstand a longer amount of time, longer lifespan, and the reusability of concrete structure in itself, it is a very important topic. So maybe you want to think of buildings that where the main structure it is kind of fixed, but all the rest of the design and facade elements and internal parts and so on can actually be replaced from time to time, also to keep updated with new standards. So I think we go in a different direction there. But also something I need to add is that wood and timber and concrete are extremely different materials. So our digital toolset, it is extremely different. So we use different type of algorithms. Everything about wood is about connections. So you need to figure out how to connect elements in a way or the other. When we're talking about concrete, it's more about continuity and having shape optimization and so on. So I would say that's the main difference from a tectonic and design perspective.
Thank you.
Yeah, thank you.
Thank you, Architect, for your answer. If there is any other questions, please raise your hand. Well, if there is no any questions, we would like to thank you very much, Architect, for allowing us to listen and learn more about your work. And thanks to the participants for attending today.
Yeah, absolutely. It was a pleasure presenting, and I just want to thank you for the invitation. And if at any point any of you have questions or would like just to reach out, feel free. I'm quite approachable, I would say. So feel free to reach out anytime, and it has been a pleasure. And I hope you have a great competition design, and would be happy to see what kind of entries you get and the results of the competition.
Oh, nice. Thank you, thank you, and thank you for all.
Thank you, everyone.
Thank you. Have a good evening or good day.
You too.
Bye-bye. Bye-bye.
Bye-bye.